and the ocean acidification sustainability along the East Coast. And I will move on with some emphasis on some case studies in Northeast waters, and this including some longshore transport as a result of the Labrador coastal current in the region. And also I'm going to show you some data, kind of latest data about recognized saturation, undersaturation in the bottom water of Wilkinson Basin. And then there's another important process. I'll just briefly touch base on it. It's just one important kind of unique process along the in the Northeast water, which is the cross-shelf exchange of material at New England Shelf Break. So, so as the CO2 in the atmosphere increase, the more CO2 being forced into the ocean. So the effect of that is what we call ocean acidification. So once CO2 dissolves in water, it goes through a series chemical reactions. The net effect is that the acidity will increase and the carbon and ion concentration will decrease. Along with that is the increase of CO2 concentration. So this system is complex. So it's not just the pH, it affects many other parameters. So primarily we use 4 parameters to describe the system, and then you need which is listed on the right side of this slide. And you need 2 parameters to basically define the system. I mean, define the system, basically you can solve the system mathematically. For related to ocean acidification, one very important parameter or indicator is calcium carbonate saturation state. So when this measure is more than 1, so chemically it favors precipitation of calcium carbonate. If it's less than 1, it's the opposite. It's basically a dissolve. Chemically, it starts to dissolve calcium carbonate. So this could be a concern for many shelf-building organisms. That's why a lot of shellfish industry have a lot of stake in this. Another very important measure from chemical point of view is that the buffer capacity of seawater. So this is the ability of the solution to resist the change in pH or other carbonate parameters when CO2 increase in the seawater. So we use many, we can use many factors to describe this, or mathematically to describe the. Oh, excuse me. Where this goes. All right. Sorry about it. I think my computer has a little hiccup here. So there's many buffer factors we can use to describe this buffer capacity. And then one of very famous one is the Ravel factor. And then there's many others. So this plot basically plot a buffer. The y-axis is the buffer capacity. On the x-axis is the DIC concentration. And then in this plot, they purposely hold the alkalinity constant. Because that's what happened in the ocean acidification case. The alkalinity of the seawater does not change, but the DIC will increase. The buffer capacity will decrease. So and then you can. So other than the buffer factor, you can also simply use DIC to alkalinity ratio to describe this. So which is, I should kind of show briefly in this slide. When the alkalinity equals to DIC, the buffer capacity reaches a minimum. So we are on the left side of this point right now, and it's for the surface ocean. And then so the effect of the ocean acidification basically is to decrease the buffer capacity of the surface ocean. So this is to make the seawater more vulnerable to CO2 increase. So that's some basic. I'm going to use this to compare regional differences along the east coast. So in the open ocean, the ocean acidification being well established. So this is the two. On the left panel is the time series observation at the time series station Aloha near Hawaii between 1988 and 2007. And so the top graph shows the PCO2 increase at surface ocean matched or pretty much follow the atmosphere CO2 increase. And at the surface, and then you see that pH decrease at the speed about at the rate about 0.001 pH unit per year. And then this decrease can penetrate up to about 1,000 meters, and below 1,000 meters, at least at this side, there is not much of a change in terms of pH or other CO2 parameters. On the right side is the time series station at the North Atlantic, is the BATS near Bermuda. And then basically it shows a similar rate, maybe somewhere in terms of pH on the order of 0.0012 units. So for the coastal ocean, this is the a slide I steal from Dwight Hill 2008 papers. It shows the ocean acidification rate in the Great Caribbean region. So this is the year between 1996 and 2006, and the picture shows the aragonite saturation. So over the 10 years, aragonite saturation decreased by 0.012 per year, and then the DIC increased by 1.2 micromole, and the rate is slightly higher than what observed in the open ocean. Or similar, not too much difference. So back in 2007, so NOAA started this first trans-regional or coastal carbon study along the North American coast. So basically two cruises in this, and one is on the west coast, the other one is on the east coast. On the east coast is we also call the Gulf of Mexico and East Coast Carbon Cruise, so GOMAC. So I'm going to basically show some of the data from this cruise. So the goal of both cruises are, the first is to kind of establish the baseline conditions of relevant carbon inventories and budgets, so that the future changes can be compared against with, this including ocean acidification. And the second goal is to provide a snapshot assessment on the distribution and fluxes of carbon and associated geochemistry across geographic boundaries. So this is the kind of the first time we look at the carbon picture along both sides in a kind of holistic way view. So in the past, we've done regional studies, so we don't have much idea of how the process across the boundary, how the process cross-boundary interact. So that's one major goals of this trans-regional study. And in the meantime, it provides a comparative view to look at the different regions. And then the result from the West Coast, this picture probably everyone saw that many times. It produced this very important paper about ocean acidification on the West Coast. And on the West Coast, many people already know that it is a upwelling driven system. So in other words, the low pH and low aragonite saturation, water from deep ocean can upwell to the shelf, and then the effect of that is make the shelf water more corrosive. With acidification, and this corrosive water can reach shallower, and also it happens the corrosive water can happen earlier than the case without acidification. So along the East Coast, the East Coast is very different in terms of physical setting. So the East Coast is a west boundary margin. In a sense, there's a major current flow along the shelf break. This is the Gulf Stream system. So in the Gulf of Mexico, it is the loop current, and then it exit loop Florida Strait and become a Florida current. And then at the end, it bent off from North Carolina near Cape Hatteras and to the North Atlantic Ocean. So this is a very important feature on the East Coast. Another very important physical setting is that this Labrador coastal current flow across the Gulf of Maine and into a Mid-Atlantic bight, and then finally bend it near North Carolina as well and into the deep ocean. So it's end there too. And then for this study, we sampled basically 9 cruise transects, and then cover 6 regions, which is in the red. So Gulf of Maine, Mid-Atlantic bight, South Atlantic bight, and so on. And then I labeled the transects as the white found as the kind of the neighboring state. So it's, for example, the Gulf of Maine one, I labeled as New Hampshire, and then near Woods Hole is the Massachusetts MA transect, and so on. So the first, I would like to show you this mixing diagram. So this is the TA salinity plot. So in general speaking, alkalinity shows conservative feature, and it's very useful for us to use it as the way to identify major water masses. So there are basically 2 mixing regimes. One is, and then both both scenarios has a common ocean end members. So in one line, it mixed this ocean end member mixed with Mississippi River plumes, which is on the upper left corner of this. And then the rest of the data falling, this is including east of Florida, South Atlantic bight, Mid-Atlantic bight, Gulf of Maine, all falling on the lower mixing line. And then if you look at the picture D in this panel, this is the distribution of alkaline and salinity in the Mid-Atlantic bight and Gulf of Maine. So this is very relevant to what we talk about here. So besides the high salinity, high alkalinity, and the low salinity, low alkalinity end members, there are some minor end members. One is the green circle I have. This is the slope water. This is primarily the deep water coming in to the shelf break and mix with the shelf water. And then there's another feature. If you look at the salinity around 32, you see this band. So we think this come from the Labrador coastal current. So that, in a sense, that current introduced a third end member. So that's why it bends down a little bit. This is if you look at, this is the primarily New Hampshire line and the Massachusetts line. All right, so this is a cross shelf distribution of the ratio, alkaline to BAC ratio, overlaid with aragonite saturation. So it's in contour lines. So as you can see, as I mentioned before, this ratio basically gives you a sense what is the buffer capacity of the shelf water. So one immediately feature from this plot is that you can see in the southern part of the shelf, like in the Gulf of Mexico and the east of Florida and Georgia, the buffer capacity of shelf water is relatively high. And as you move to the Massachusetts line and New Hampshire line, this buffer capacity is relatively low. And the highest buffered water you can find is in the plume of the Mississippi River, and the lowest buffer capacity water you can find in the bottom water of Wilkinson Basin, basically at the bottom of this plot. And but in general, less than 2 is considered to be relatively low in this situation, and then as you can see, Northeast water in general has very low aragonite saturation state. Another very important feature is that you can see that this ratio, the aragonite saturation pattern match the buffer capacity very well. And then this is because this ratio basically can predict what is the concentration of carbonate ion concentration. And then we know carbonate ion concentration is proportional to the saturation state. So that's why we have this very tight relationship. And this is a summary of the regional difference. And on the y-axis is the different parameters of carbonate system, and on the on the x-axis is the location or the transects. So I like purposely sequence this as from Texas all the way to Gulf of Maine or New Hampshire. So if you look at the figure A, then the alkalinity is in blue. It's relatively high in the southern shelves, and then after Georgia, it's a steadily decreased. So this is this is the mean shelf water condition. So basically, this is the mean alkalinity of the water on the shelf. And as the alkalinity decrease in the northeast, we don't see much of change in DIC, in the mean DIC concentration. So because of this pattern, you have this TA to DIC ratio generally follow the TA pattern with a little exceptions maybe in east of Florida, where there's a small upwelling event occur during the cruise. But other than that, it's basically follow the alkalinity pattern, and so it's relatively high in the south and low in the northeast. So because of the prediction power of this ratio, and then the alkalinity, aragonite saturation basically follow this pattern, as well as the pH and CO2 fugacity. But in the CO2 fugacity, that's the chemistry to that. And then we also see a large decrease in terms of temperature from Gulf of Mexico all the way to New Hampshire. There's basically 17-degree drops in temperature, which is in the panel D. And this decrease only counts about 15% of the change you observe in aragonite saturation. In other words, most of the changes you see in aragonite saturation is due to the difference in seawater composition, namely this TA to DIC ratio. So we see this very different. We see this original differences, and then what that really means. And then this is kind of a example to show that what that implies. So if you have a mean conditions of seawater in the northern Gulf of Mexico, which is listed in the table, and then you increase the PCO2 in the water, assume that's kind of the case of ocean acidification. So that will lower the seawater acidity pH, or increase the acidity of seawater by this much on the right side of the screen in the first row or second row of the table. And then if you apply that same amount of increase in PCO2 and apply that to the Gulf of Maine mean condition seawater, you found that the acidity increase is 14% more in the Gulf of Maine than in the northern Gulf of Mexico. So this in other words, you apply the same changes because this buffer capacity difference and then the chemistry difference, then the pH change or the acidity change more in the northeast waters. And because of this, and then plus there's a low temperature. So in other words, the northeast waters has low water temperature, and it means it has a higher CO2 solubility. It will absorb more CO2 into the water. So all of this indicate that chemically these waters are more susceptible to acidification if the acidification continues. So the next I would spend a few minutes to talk about the processes that important to shape the distribution of the carbonate system along the east coast, northeast coast. So one of the important processes I'm talking about is the longshore processing as a result of the Labrador coast current. And then, so the goal here is to we know this coast current is very important, but we want to know, when this current flows through the region, it will introduce mixing, and then along mixing there will be biogeochemical processing. So we want to see how much this mixing versus biogeochemical processing, contribute to the change of carbonate chemistry on the shelf. So to do that, we make two assumptions here to make the case simpler. One is we assume this longshore flow is dominant. This is a relatively safe assumption because the transport volume of this current is much larger than the freshwater input in the region. And the second is we assume this system is steady state. So if we do those assumptions, and then we look at the data from the GOMAC, and then we found that the mean conditions from New Hampshire line to North Carolina line. So this is the mean flow, and then we found the salinity increased by 3 units, and in the meantime, alkalinity increased by 130 micromole, and DIC does not change much. You can see the circles in the plot basically shows the trend as this flow from New Hampshire to North Carolina. So given alkalinity is conservative, so that the 130 micromole changes, it can be converted to the mixing effect. So it's and then if you use a mean PA to DIC ratio, and then you can convert this mixing effect from alkalinity to DIC, so which is corresponding to 120 micromole of DIC. And then to derive the biogeochemical process, we use this salinity normalized DIC equation. It basically removes the salinity effects or mixing effects, given also the equation also takes into account of the freshwater end members. So if you do this exercise, and then you find from New Hampshire to North Carolina, the DIC decreased by about 80 to 90 micromoles, and then if given 20% uncertainty, this value it's about the same magnitude as the mixing, as I listed above, but it has the opposite sign. So in other words, the mixing effect is increased the DIC concentration, about your chemical processing is decreased. Actually, we do see that the mean shelf DIC does not change much from New Hampshire to North Carolina transects. So this is kind of consistent with what we come up with in this analysis. And so the next case is I'll just briefly talk about the recognized undersaturation in the bottom water of the Wilkinson Basin. This is the new data we just collected in May, and so the idea is we want to follow, we know the pH and recognized saturation are low in the Wilkinson Basin based on the GOMAC data. So we want to see whether those waters has already experienced undersaturation conditions. So and the matter of fact is we found that yes, it does. in this data, this is the profile collected right near the end of spring bloom, and at the bottom near 250 meters, you do see the aragonite saturation is near or slightly lower than 1. And the pH in situ condition is less than 7.8. So this is quite a low pH and a low aragonite saturation. So this is just a pilot study, and then we are going to continue this and see what the seasonal variability there may be. And then those corrosive water corresponding to this BNL or nephron bottom nephron layer position. So this is the profile from the cruise, and if you look at the black profiles at about 250 meters, you see this high beam transmission. Low beam transmission values. So those are corresponding to the BNL layer. And so there are some. We have some hypotheses about this, but because of the time constraint, I don't have too much to get into the details. But in general, we think it's probably because we have the spring bloom at the surface, and then the fresh organic matter settle down to some of those deep basins, and then when they do that, and then it remineralize, and then that process decrease pH and increase the CO2 at the bottom water. And you can kind of see from historical data from this sediment traps. So this is the data I got from Pilscomb, Cindy Pilscomb from UMass Dartmouth. So they see high PUC flux during the bloom area. And then they saw, both at the surface and near the bottom, the BNL layer. But in the meantime, when the POC flux is high, the calcium carbonate flux is actually low, and then that's kind of consistent. And we see, the low pH conditions. We see the data we show, and this is the location not far away from our station. So the hypothesis I just lay out is probably because we have under saturation condition in these patients that probably keep the calcium carbonate flux low near the bottom. So the last case, I think I have a few minutes, and then just the last case is the cross-shelf exchange at the New England shelf break, and then this is the same data set I show. And then just give you a sense where there's a strong cross-shelf gradient, which you can see from this cross-section plot. So on the top panel is the top plot is the salinity contour on the alkalinity distribution. So across this strong gradient or frontal structure, there's a decrease of salinity about 2 units, and then there's about 200 micromoles of change in terms of alkalinity. And there seems to be, if you look at the bottom figure, that there's a net transport of carbon from the slope water onto the shelf, and that's why you see a high DIC concentration near slope, and then in the meantime you have low pH water. And this is the data collected in the 2000s by Burkill's group, and then this is the kind of very high resolution carbonate data. And then you can see on the outside of this line, which is the front shelf break front, and you will see low PCO2 low PCO2 and low DIC at surface, but it's high at the bottom. And on the onshore side, you see low alkalinity water, but a high PCO2 water. at the bottom. So what they calculate, there are basically two potential ways that carbon chemistry can be affected. One is it can through vertical transport. The other one is the cross-shore transport of material. So they did some vertical transport calculation and found that's quite significant. But so far, we haven't been able to calculate the cross-shelf transport. So this is something we want to do in the future, and because we think that's probably very important to the shelf carbon chemistry. So before I give a very end slide, I just want to show a slide that I got from Conservation Law Foundation. This is a opinion survey, they did in the New England. So just look at the perceived threat to the ocean in the publics versus the issue of visibility. So as you can see, like global warming, for example, has a high perceived threat and then a high issue of visibility. But on the other hand, in New England, the ocean acidification it has very low visibility. So traditionally, I think people think because this is the west margin, west coast margin, and so the upwelling is a relatively weak phenomenon, and because of that, they tend to think that the acidification is not an issue. But the data I just showed that indicate that the northeast water is probably is more susceptible than what we originally thought. So this is just give us some bullet points of kind of take-home message. So and you can read through it. And so essentially, we found that the northeast coastal water it kind of more susceptible than the rest of the east coast. And then there are longshore mixing and biogeochemical process are very important in this region. And there's already have under saturation conditions in the bottom water of Wilkinson Basin. And at the last, then the cross-shelf exchange at the shelf break may play a very important role in shaping the carbon chemistry in the Indo-Atlantic bight. So I guess I'll stop there and take questions. Thank you.
Thank you very much, Alec. So if you have any questions for Alec, could you please just type them into the questions panel or the chat panel, and we can relay them across. At the moment, there's nothing in there, so but please pass across some questions if you have any. Well, everybody seems to be shy of typing that in. Okay, so the other way to do that, it would be to raise a hand. If anybody wants to raise a hand, I can try and unmute you, and then we can ask some questions directly. Well, I think everybody seems to be very satisfied with what you have presented today.
Okay. All right, thank you.
Very much for your time, and thank you all for joining today. Any questions, comments, thoughts, please send them along. And I think we have another webinar next Tuesday at 10 o'clock. So I look forward to seeing you all again, and thank you for joining us today.
Thank you.
Oh, hang on a sec. We have one question here. Is your cruise annual, and what will be needed to characterize CO2 in an annual cycle? And that's from Beth Turner.
Okay, so the cruise, which cruise you talking? If the GOMAC cruise is every 5 years, so there's a second GOMAC cruise last year. In terms of our cruise, we've done like 3 cruises so far. I showed the data in the Gulf May. So it's from May. That's the first cruise actually. We did some summer cruise, and We intended to do it again in the spring. So basically, we try to cover the seasonal patterns. So that's our cruise schedule in terms of that. We still have to figure out how to pay those cruises fully. But anyway, what's the other question? The PCO2 what? Sorry?
What will be needed to characterize CO2 in an annual cycle?
What would be need to characterize the annual cycle? I mean really, if you want to do good coverage, if you want to have a good coverage, you have to measure the common chemistry, maybe on a monthly basis at least. I think if you have a sensor, then that will be good to use. And then I don't know exactly what this question goes to, but there are 4 parameters you want to measure, and then pH and the PCO2 are people using sensor to measure those, and then there are the other like alkalinity and DAC. They don't have a sensor. You have to rely on bottle samples. So more frequently you can go up there to collect the bottle samples. That'll be better. The reason you want to do the DAC and the alkalinity is because the pH and PCO2 often is not a good pair to calculate the CO2 to solve the CO2 system. So you will need either DAC or the alkalinity to do a better job. That's why a lot of time we want to use DAC and alkalinity. But we are developing DAC sensors at this moment. So we are in the middle of testing the new sensor, but those sensors only available through collaboration, not through commercial ways. So I don't know whether I get to the point of the question.
Beth says thank you, so I think you did. Are there any other questions for Aleck today before we close this down? At the moment, I'm not seeing anything. So I'm going to say thank you very much, Aleck, from me and from all of the rest of the steering committee of NECAN. Thank you for spending your time with us today and sharing this. And for everybody else, and you, Aleck, we look forward to seeing you again next week. So everybody have a good week and a good rest of the day. Thank you.
All right. Thank you. Thank you for having me.
Goodbye.
All right. Good night.